All right, so let's combine some of the things we learned to find a property of a molecule, and that's the polarity of a molecule. So think back to when we first started Lewis structures, we said covalent bonds can be polar, and so they have uneven sharing of electrons. Fluorine is more electronegative than hydrogen, and so the electrons spend more time on fluorine, and so fluorine overall is a polar molecule because it has a dipole moment. There's a partial positive on hydrogen and a partial negative on fluorine. So it's kind of like a magnet with a positive and negative end. Let's take a look at another molecule, CO2. And so if you think about the dipoles of CO2, carbon is more oxygen is more electronegative than carbon. And so the dipole, there'd be one right here and then one right here. And so you may think that because it has dipoles that it has polar bonds that it's going to be a polar molecule, but that's not actually true. If you think about the poles of this, they're opposing each other, and so it ends up being non-polar. Think about water with its bent shape. Oxygen is obviously more electronegative. And so you can see here the dipoles are pointing in the same direction. And so there is a net dipole going like this. And so this molecule is indeed polar. Water is a very, very polar molecule. Another example, carbon tetrachloride with its tetrahedral shape. If you think about all of these dipoles, chlorine more electronegative. So they're all pointing away from each other. And so since they're pointing all away from each other, they're all going to cancel out, and so that it's going to be non-polar. Whereas something like carbon with one fluorine and then the rest hydrogens, remember a CH bond is generally considered non-polar, so there's only one dipole here, and it goes like this. And so since there's only one, it ends up being polar. So in general, it's what's called vector addition. So if you have dipoles that are facing opposite directions, either going into each other or going away from each other, they cancel out, and so there's no net dipole, and so it becomes non-polar. And then if you have them kind of facing the same direction, or kind of even approximately the same direction, they're going to sum together. And so there will be a net dipole, and this molecule will be polar. And so the polarity of molecules determines a number of factors. One of the things is what it's going to dissolve in. So this old saying goes, like dissolves like. And so what that means is polar things dissolve polar things, non-polar things don't dissolve non-polar things dissolve non-polar things. And so example of this is oil and water, right? Oil and water don't mix. Oil is made of mostly CH bonds, and so it's non-polar. Whereas water is H2O, and we already covered that is polar. And so if you have something that's polar and non-polar, they're not going to mix. The analogy I like that they use here on this side is that the polar molecules are like magnets, so they've got a positive and negative end. And then non-polar ones are basically just like regular marbles. And so if you think about if you mix a bunch of magnets and a bunch of non-magnetic things, all the magnetic things are going to stick to each other, and the non-magnetic things are not going to stick to each other, right? And that's because if you have HF, right, you have this partial positive, partial negative, and then if you think about the way these things are going to want to stack, opposites attract. Kind of a little confusing with the like dissolves like, but opposites attract. We're talking about different things here. And so it's going to want to maximize the interactions between the positive and the negative bonds, right? So you can see there's an interaction here, positive, negative, positive, negative. Cool. So just some things to note is increased polarity generally has increased melting and boiling points. That's pretty much the only thing I want you to know. Be able to identify a molecule as polar, and then know that polarity increases the melting and boiling point. So pretty cool that we're getting into the investigation of the properties of atoms.